We will continue looking at the specification of spatial regression. So far, we've looked at the way in which spatial covariance can be obtained either directly or indirectly through a spatial process. And now we're going to move to specific spatial regression models. And we'll start by a quick review of spatial stochastic processes, primarily, again, putting into context what I just mentioned about the relationship between conditions, conditionals, marginals, and joint densities in the specific context of a spatial process model. And then we move to three particular specifications: the spatial autoregressive model, the conditional autoregressive model, and the moving average model, the spatial moving average model. And for each of these, we'll see the basic specification in matrix notation and then the covariance that follows from that. And then very quickly review the spatial lag and spatial error model. I touched upon this briefly yesterday in the introduction, but we'll just have a little more detail on it today. And then if there's time, I want to give a very quick discussion of how we relate these models back to different notions of spatial externalities, which is the substantive interpretation. The spatial process deals with what is called a spatial random field. And that's really, as I like to say, a figment of our imagination. It's a mathematical concept through which we try to model the randomness in spatial locations. That's why it's called a field. So in essence, it's a model for a collection of random variables, a collection of z at S, where S is a location. And then depending on how we index that location, we end up with different classes of models. As we saw yesterday, the event data versus the continuous surface data versus the discrete spatial locations. Each of these would have a different formal expression for S being location as an element of a collection of possible locations, D. So this collection of possible locations could be a finite set, or it could be an infinite set, for example, when we deal with surfaces. And then what spatial processes are about are mathematical, formal descriptions of what this collection of random variables is and how it behaves in some sense across space. So it's about, and it's very important to appreciate this, it's about the pattern as a whole. As I mentioned a couple of times already, in a cross-sectional situation, we really only have one observation, one data point. The data point is the pattern. And the pattern is, if you wish, one realization of a joint multivariate distribution. So you can think of some machine behind the wall that generates data in spatial locations, and we just happen to see one snapshot of this. Now, if we had multiple snapshots, then we could derive from that what the actual distribution is of the data, the distribution that generates these patterns. But we only have one snapshot. So the way we will cheat, if you wish, is by imposing structure. And at the end of the day, we will deal with our spatial observations as if they are separate observations, but in fact they are not. And the only way we can do this is by assuming a lot of stability, a lot of equilibrium, this notion of stationarity, if you wish. So the different models are ways to approach and formalize the uncertainty in the spatial distribution, either jointly, everything together, or conditionally, and then building up from the condition to eventually get the joint distribution anyway, because that's what you need. Let me digress 1 second how the stationarity works. We'll get back to this when we talk about estimation. If you can imagine a system that is stable and that generates a similar map each time, not the same map because it's random, there's stochasticity, there's randomness involved, but it's a similar map. So let's assume we see 20 of these maps and there's 20 locations. Now, if there's really a stable system, then it shouldn't matter whether we look at each of these 20 maps separately, or we look at one location in map 1, the second location in map 2, the third location in map 3, and so on. And that's the trick behind stationarity. So if the system is really stable, then we can conceive of the particular map that we're looking at as being made up of location 1 taken from our first map, location 2 taken from our second map, and so on. So in essence, if the system is stable enough, it doesn't really matter whether we see all 20 of these maps or just one. And that's the trick. Now to get there, of course, it doesn't just happen. We have to assume a lot of structure. And that's the stationarity. Stationarity meaning the joint distribution doesn't change. That's essentially what it's about. How we get at these models is through a model for the distribution of the data. The simplification that we introduce is that the conditional distribution for the value at each location conditioned on all the other locations can be simplified. And that is called, and you will see this in the literature, a spatial Markov field. Very similar to a Markov process over time. Markov process over time says, what I know about a variable today, given its whole history, is the same as today given yesterday. That is a Markov property. And so then from this conditional distribution, you can build up the whole joint distribution. Now in space, it's not that easy, as we'll see in a few minutes. But the Markov property is the same. It's essentially simplifying the conditional distribution. So a value at one location given all the other locations can be simplified by the conditional probability of that location given only a small number of neighbors. So we can cut the other ones out of the conditional distribution, which is the same logic we're following with the weights matrix. Remember, with the weights matrix, we define a small number of non-zero elements, which are the neighbors. And that's kind of the thinking is similar to this spatial Markov field, where we start by conditioning on immediate neighbors, and then by pulling all these conditional distributions together, we hope we get a model for the whole thing jointly, which is the joint distribution. So how can we do this? The challenge is, how can we make a joint probability from the conditional probabilities? In time series, there is a thing called a factorization, where you essentially move backwards. You say, today conditional on yesterday, yesterday conditional on the day before conditional on the day before that. And you multiply it all together, and it gives you the joint density for everything, for all the days at all times. In space, it doesn't happen. It doesn't work, as we already saw, because me conditional on my neighbor, and then the neighbor conditional on its neighbors, but I am one of those neighbors, so I get back into it. So it doesn't factor out nicely, which is the main problem. So how can we come up with a factorization? And as I said, I will spare you proofs and theorems, but this is just a term that you should know about. This Hammersley-Clifford theorem spells out the conditions under which we get a factorization in a spatial Markov process. And it has everything to do with the structure of the neighbors. And in a nutshell, what it boils down to is restrictions on the kind of distribution that we can use, Gaussian normal distribution or more general exponential family, and limitations on the spatial weights. And the one that affects us the most is that the spatial weights matrix has to be symmetric, which excludes row standardization. Row standardization if there are an unequal number of neighbors, will yield asymmetric matrices. Say if one observation has 4 neighbors, the weights are 1/4. Another observation has 5 neighbors, the weights are 1/5. If these share a common neighbor, the one weight will be 1/4, the other one 1/5. And that's asymmetric. So you can't have that in this to get this factorization. So to get the factorization of conditional models, you have to have symmetric weights. Now if you're comfortable with that, that's fine. If your model requires asymmetric weights, you cannot use this approach. You have to use a different approach. Okay. The Hammersley-Clifford theorem, as I mentioned, is also the basis behind Markov chain Monte Carlo. It spells out the conditions under which you can get the joint density, which is the one on the left, by a series of products of conditional densities. Okay. And these conditional densities can get quite complicated, but the whole trick is how to come up with a structure that is manageable. Okay. And in space, what we're interested in is how many neighbors do we need to condition on to get a manageable system that yields us, in the end, by multiplying all these things together, yields us a proper joint distribution. This is very hard to read. It's a very difficult theorem. In fact, it didn't have a proof for the longest time. It was never published. It was referred to by Bisag in one of his early papers, and it is fundamental behind the conditional modeling in space.
Could you reiterate about the weights? What, they must be symmetric. Why does it exclude row standardization?
Okay, row standardization, the number of neighbors is not constant. Row standardization is obtained by dividing each one by the number of neighbors. So when the number of neighbors is not constant, then you get different values in different rows. Okay. And because observation I has 4 neighbors, say, that doesn't mean that the observation J, that is one of those 4 neighbors, itself has 4 neighbors. Say if J has 5 neighbors, then its weights will be 1/5, including the Wji. See, Wij will be 1/4, but Wji will be 1/5, because it's determined by the number of neighbors of J, not the number of neighbors of I. So if they are not the same, then the matrix becomes asymmetric.
So if you have the same number of neighbors, row standardization would be okay?
Yes.
Okay.
Yeah. So if you have like k nearest neighbors, but that doesn't work either because the k nearest neighbor relation is not symmetric. So the conditional models are, I don't want to make too big a deal out of this, but they are more restrictive in some sense than the simultaneous models. In a simultaneous model, you can do anything you want. In a conditional model, because you're in fact exploiting information about the neighbors, you can't do anything you want. You have to play by the rules in order to end up with a proper model for the whole pattern, or for the pattern as a whole. Okay, so when you play by the rules, this is very attractive, because these models tend to be much simpler. And they tend to be, you can estimate them by simpler techniques than the simultaneous models, and that's very attractive. But if your substantive question does not agree with symmetric weights matrices, then you're in trouble. Then this is not an approach to use. Now, one of the reason I stress this so much is that a lot of the Bayesian work, the Bayesian hierarchical models that deal with spatial correlation, they all use conditional specifications, because these models don't have analytical solutions. They're all estimated by means of Markov chain Monte Carlo, Gibbs sampler, those kinds of things. And for the Gibbs sampler to work well, you want a nice conditional formulation. The simultaneous models are much more complicated, and we won't have actually talk about this in this course, but in the frontiers one, I'll show an illustration of how much more complicated a simultaneous hierarchical Bayesian model is relative to a conditional one. And the reason I stress this is that in practice, a lot of use is made of Winbugs, for example. Winbugs has very nice capability to estimate spatial hierarchical Bayesian models, but they're all conditional models. So if that's fine with you, there is no problem. But if your substantive concern requires asymmetric weights, for example, if you want to use k nearest neighbors, then you cannot use these types of frameworks. And so that's a limitation in some sense, or for some cases it's not a limitation. One thing that you also see in these hierarchical models is much more direct representation. So the covariance matrix becomes a direct function of the distance. So then you have the symmetry by construction, because that's how you set it up. And what is important is that you appreciate that these are all different ways of modeling spatial dependence. They're not competitors in some sense, because they're each appropriate for a different purpose. And if your purpose doesn't match the assumptions that the specific method requires, then you should use a different method. And this is where I have some problems with this sometimes, in that because the software is there, all of a sudden everybody does these conditional models, even in instances where it really is not appropriate for the process that you're modeling. But it can be done, and there's lots of other processes where it's totally appropriate, but it is something you have to keep in mind. And to illustrate the differences between these processes, I'm just going to go fairly quickly through the same exercise for each of the three major classes. So we have the simultaneous spatial autoregressive models. I will show you the specification. Use a artificial example of a little lattice with 6 observations, stick in some values for the parameters, and come out with a covariance matrix. So we'll do that 3 times, and then we'll see how the spatial covariance structure differs between models that you might think look the same, in the sense that the parameter for the spatial process is the same value. So in each of these models, the row, if you wish, will have the same value, but the covariance that follows from it will be very different. And that's something that is important to appreciate at the stage of specifying your model. What is the kind of covariance that I want? And in function of that, you take a different model specification. Let's start with the most commonly used one, the spatial autoregressive model. And we've already seen this in the previous example. What I call a pure spatial autoregression is something that is actually not very useful, but it's useful as an example to set the stage, if you wish. In an actual modeling situation, this just says the values depend on themselves and pretty much nothing else. So if you solve this out, as we do in the reduced form, you see that in essence the pattern of the y is simply a transformation through this inverse matrix of a random vector. And nobody ever saw a random vector. You don't see random vectors. You see realizations of random processes. You might see the y's, but you don't see the u. The u is just some structure that we put in a mathematical model. So that's why I say this model is actually not very practical, because it just shows you how you get pattern out of randomness. For example, the pictures I showed you yesterday of the 10 by 10 spatially correlated grid cells are obtained in this fashion. So you start with a vector u of 100 standard random normal variates, and you pre-multiply that by this I minus rho w inverse matrix, which is a 100 by 100 matrix. and out comes a realization of the process, the y values that you can then stick on the grid, and you see as you increase the row value, you saw more and more clustered patterns in the pictures. The importance is, and this we've already seen it too, just rehashing, if the mean is 0, we don't actually have to worry about it, and then the covariance takes this form. Important in this form is that there is an inverse involved. So no longer sparsity, we have a full matrix. Now let me go to the example, which is the same one I used yesterday, of the layout of the 6 polygons with the first order contiguity weights matrix on the right, the zeros and the ones. And we will row standardize this and use a parameter value of 0.2. We solve the whole inverse thing you just saw, and then out of this comes this nice invisible matrix. Again, the things to notice about this is that the diagonal elements, even more so than in our line example, because there is more variability, if you wish, in the structure that we use here, the diagonals are clearly non-constant, and then the rest is kind of a mess. There is some pattern in there, but it's nothing like what you see in the time series models. Also, there are no zeros in there. Everything is non-zero. And look at the numbers. They are fairly high. If you standardize these to make it into a correlation matrix, you see that the spatial correlation between first order neighbors is of the order of 0.68, and then we have values of 0.25, 0.44. These are all fairly high values. Just keep this kind of as a reference, because now we're moving to another model which will look exactly the same, but it's actually different. This is the conditional autoregressive model, and this starts with a conditional expectation of the value, the conditional mean of y at I, conditioned upon all its neighbors. And this is a Markov model, so it says we don't actually need all the neighbors, we only need the ones for which wij is non-zero. And we specify this relationship as a linear relationship, which works fine if we have a normal distribution. Once we walk away from the normal, then this linearity becomes problematic, or can become problematic. So the Hammersley-Clifford thing again allows us to move from this to a joint distribution, and the covariance in the joint distribution takes on this form. And I'll spare you the details, but if you want a specific discussion of this, the Cliff and Ord book has a very nice example that shows you how you get from this linear conditional expectation to the covariance form. And indirectly, we see here why W has to be symmetric. The covariance is no longer a cross product. In the previous one, it was a cross product. I don't know if you remember, but it was I minus rho W prime, which is transpose, times I minus rho W. That is always symmetric. A cross product like that is always symmetric by construction. There's no cross product here, so there's nothing here that guarantees the symmetry unless W itself is symmetric. And that is something that needs to be respected. If you don't make W symmetric, then you end up with a covariance matrix that will be asymmetric, and that you can't have. Okay. So we'll do the same thing. We have the model. We stick in the parameter value, same row 2, and then out comes the covariance matrix. Again, we see the variances are not constant. We see the off-diagonal elements. And I need to take a break here. Battery's out. Sure. You don't want to be
I know,
taped.
I just limit on how many I can ask, but, in your
Yeah, the
example-
counter is on.
Yeah.
And,
In your example, you have the layout and the weights matrix, and the blocks are numbered 1, 2, 3, 4, 5, 6. Did you actually use numbers for the data, for the Ys?
no, the data are the same standard normal variance. So I have 6 standard normal U's. Actually, I don't need them in this case because I don't actually have the Y. In the example before, I did have Y's, but in this one, I don't.
Yeah, but
I just go straight to the covariance
yeah,
matrix.
the one before is what I was talking about. So you just pulled 6 standard normal U's
Yeah.
and used those.
You take 6 standard normal U's, you
Yeah.
pre-multiply them by I minus rho W inverse, and that gets you the Y's. One for location 1, one for location 2, and so on.
Using econometric terminology, would it be correct to say the difference between SAR and CAR is in SAR, the lag neighbors are endogenous, in CAR, you can treat them as exogenous?
Exactly, yeah. And this is the essence of the difference between the estimation methods. In that the SAR, you have to deal with the endogeneity, the simultaneity. In the conditional one, you don't, because you've essentially assumed it away by the structure of the model. Yes. So if we move on and look at the corresponding correlations, you may notice that the numbers are much smaller than in the SAR model. And so qualitatively speaking, even though the parameter rho is the same, it's 0.2 in both cases, the correlation structure that results from the CAR specification is weaker, spatially speaking. So remember, what we were interested in when we focus on the spatial covariance structure is how strong is this covariance and how far does it reach. One thing that we see here is when we go with a conditional specification, the spatial correlation, if you wish, is weaker than for a corresponding or a matching, if you wish, simultaneous model. So with the same parameter, you could say, well, if you change the parameter, of course it would be different, but we don't change the parameter. What we're changing is whether we look at this conditionally or jointly, which then gives us a different structure for the covariance matrix, which gives us a different strength for the correlation in the model, in the pattern. Remember, the covariance structure is about the pattern as a whole. The model specification is how we get there, how we start out in order to get to the pattern. So between the two, everything else being the same, the CAR correlation structure is weaker than the simultaneous correlation structure. Also, very important, they're not the same thing. So an SAR is not the same as a first order conditional autoregressive model. The variance structure is different. Even if the SAR would have a symmetric weights matrix, which it could, its variance is not the same as for the conditional model. So you see the SAR model you can think of as a counterpart conditional model would have 2 neighbors involved in the conditions, 2 orders of neighbors. And so you can, another way to think about this is, as we saw, the conditional model gives you weaker correlation. So to get the same correlation as for a first order simultaneous model, you would need, I mean, this is not very precise, but intuitively, you would need a second order conditional model to get the same kind of autocorrelation as you get in a first order simultaneous model. And you can see this by looking at the covariance structure. There are 2 terms in there for the SAR model. One term is W, the other term is W squared. W squared, in essence, I mean, it's not exactly like that, but it includes the second order neighbors. It includes some first order neighbors as well, but that's another story. So it's actually not as simple as it sounds, but roughly speaking, to get a conditional model with the same strength of spatial correlation as a simultaneous model, you need more orders of neighbors included in the condition. So you need to go further out in terms of the Markov property, in terms of the conditioning on the neighbors. And vice versa, a conditional model is not a first order model. In fact, you can make a conditional model that matches it, but it is a different interaction structure. You have to decompose, because we no longer have a nice cross product, we just have this single matrix. We have to take, if you wish, the square root of a matrix, which is a Cholesky decomposition, which turns the matrix into a product of two triangular matrices, an upper and a lower triangle, and you multiply these two together, then you get this one back. So one of these triangles is called the square root, or the counterpart of a square root of a matrix. It's a Cholesky decomposition. So if you do that, then you can get a conditional model that matches that, but it's not an operational thing. It's not something that is very meaningful. Okay, both of these, as we saw, are global processes. We didn't see any zeros in the covariance matrix. In contrast, the moving average model is not a global process, but is a local process, as we'll see in a minute. If you've done any time series work, you know this already. But in a moving average is not an auto model. An auto model regresses something on itself. A moving average is a combination of, if you wish, local errors with neighboring errors. And it's some kind of smoothing. So you have location-specific errors, and then you have another component to the error structure that is kind of a smoothing or an averaging of the neighbors. And it kind of pulls down the spikes, if you wish. So the moving average structure in space consists of the location-specific element, which would be the U, and then the average of the neighbors, which is the WU. And since W has zeros on the diagonal, we're not double counting. So we have the individual, as it's sometimes called, innovation, is the U of I. And then the other ones are the neighbors, the J's, the UJ's, that are weighted by the elements of the weights matrix. And so these two together then give you the actual randomness in the pattern of the Y. Now again, this is not an operational model. We'll see later on this is used as a structure for the error term in a regression model. The error term could then be, say, autoregressive or moving average. So interestingly enough, in the moving average model, there is no inverse involved in the spatial covariance matrix. So the spatial covariance matrix is the sum of an identity matrix, so ones on the diagonal, that's this I thing, then rho times W and W prime, which is the first order neighbors, and then rho square, which since rho is less than 1 is a decay, it's smaller, times W prime, and those are the second order neighbors. But that's it. So the covariance becomes 0 for any neighbors that are further than 2 orders away. And that is another way of saying this is a local dependence, a local process. Because the only non-zero covariances are for the immediate neighbors and the second order neighbors. Again, there is no direct match between the weights matrix and the covariance structure. You might say, well, my weights matrix is only first order neighbors. The covariance structure is first and second order neighbors. Now, why is this relevant? It's also relevant, it's relevant for a number of different reasons, but it's relevant for spatial sampling. Let's say you're interested in, you're not interested in spatial autocorrelation, but you know it's there, and you want to create a subsample from the data that is not spatially correlated. So we know Tobler, we know if we go far enough away, they will not be correlated. Okay? how far do we have to go? It's a common misconception to base this on the weights matrix only. And so you have a first order process, you say, I will sample second order neighbors, because the first order neighbors are correlated, the second order neighbors are not. Well, in fact, that's not correct. Even though the weights matrix in the model specification only includes the first order neighbors, the covariance that follows from that has the first and second order neighbors. So if your true process is a moving average process with a W that is first order contiguity, then in order to sample locations that are not spatially correlated, you have to go to the third order neighbor. Because once you get to the third order neighbor, the covariance is 0. Because this expression here is non-zero for the first order neighbors, the W prime, and then for the first and second order that are included in W times W prime. That's essentially what that incorporates. And then anything beyond that is not in here, so it has 0. So if you want uncorrelated observations, you go three apart and you're in business. When the process is autoregressive, it's much more of a challenge, because as we saw, there is no of this 0 business. Everything remains non-zero. So we have to go much further apart before we get essentially 0 spatial covariances. In our little example with just 6 observations, we saw that it was impossible to resample observations that are not spatially correlated. But with the moving average process, as we'll see in a second, we can. Because if we do the same exercise again, 0.2, we plug it in, we see with some imagination that the last element in the first row is 0. So if we sample the first one and the last one, so actually it's not a line, in the layout, 1 is below here and 6 is up there. If we take those two, they are in fact not spatially correlated. So then we would have a subsample of uncorrelated random variables. And if you have a huge data set, that's a lot easier to work with than having to deal with all these spatial models. You basically resample locations, every third neighbor, and then you have a new sample that is spatially uncorrelated. And if you have 1 million data points, that new sample will still be very large. Okay. But when the process that is underlying the dependence is an autoregressive one, a simultaneous autoregressive one, then you can't really do that. Then you have to go much further before you can say these are uncorrelated. And how far? Well, you don't know. You don't know unless you estimate the model. See, we cheated. I stuck in the 0.2, and then I worked out what the covariance matrix was. In practice, you don't know that it's 0.2. And you can only know how far you have to go if you know what the parameter is. If you have estimated the parameter, which kind of defeats the purpose, because if you can estimate the parameter, then you don't need to resample anymore to avoid the problems in estimating the parameter. So this is something that you should keep in mind when you do spatial subsampling, when you're interested in eliminating spatial autocorrelation. For example, in remote sensing, this is a classic approach. You subsample pixels. Now, if there's strong autoregressive spatial autocorrelation going on in the image, then you have to be very careful in how you subsample the pixels, because they will remain strongly autocorrelated, even though they may be fairly far apart. When it's a moving average process, which is a local process, that is much less of a problem. Now these two, as we'll see when we talk about externalities, are very different in terms of the kinds of processes that we are considering. One is global. We have a spatial multiplier. What you do here affects what happens there. The other one is local. The spatial multiplier stops. beyond the second neighbor, there is no effect whatsoever. There is a much more limited notion of these multiplier, these spread effects, when you have local spatial autocorrelation. And there's nothing special to it. It's the same in time series. You know, when you have moving average, that's a local correlation structure. When you have autoregressive, it keeps going much further out. So the other thing is these correlations are back comparable but smaller than the autoregressive process, but the most important thing is the zero that pops up if you go far enough. So all of these, in a nutshell, all of these processes are heteroscedastic. I should qualify that if the number of neighbors is not constant. That's very important. When the number of neighbors is constant, then the heteroscedasticity is not a problem. Also, with direct representation, when we stick the function in there, heteroscedasticity is not a problem, because we, in an exponential, negative exponential, for example, at zero distance, which is the diagonal, we have a constant value. But in the the processes where the W, where the weights matrix is not, does not have the same number of elements in each row, then we'll get heteroscedasticity. And this is something that is has practical implications, but also theoretical implications. As I alluded to, a lot of the proofs of these central limit theorems and laws of large numbers, all these nice things that you need to get the consistency of the estimators and so on. Most of these from the time series domain assume stationarity, meaning constant variance. In the spatial domain, you have to deal with the non-constant variance, which basically means that your proofs are more complicated. And at the end of the day, you still have the same result. You get consistency and asymptotic normality, but to get there is a lot more complicated because you have to deal with this extra variability in the asymptotics. SAR and CAR are global processes. There's a dying out of the covariance, but it is can be very slow. In contrast, moving average is a local process, and beyond the second order neighbors, in this particular case, it stops. Okay, now what I want to do is go over the lag model and the error model in a little more detail than we did yesterday. Yesterday we had some sense of what this was, and what I want to do here is just give you a slightly more technical detail about the structure, and then we can use these tomorrow in our diagnostic tests and in our estimation. The spatial lag model, as I mentioned yesterday, is the one that we will be using, is not the pure form that I just illustrated in terms of the covariance matrix, but a mixture of a spatial lag term, the Wy, and a regular set of covariates, the regressive term. So we call this a mixed regressive spatial autoregressive model. We have the dependent variable y. We have a spatial autoregressive component in the form of the spatially lagged variable Wy and its coefficient rho. And then we have the regular regression part, which is x, the explanatory variables with coefficients beta, and an error term epsilon. So this is the basic formulation. The inclusion of the spatially lag dependent variable can be interpreted in a number of ways, as we discussed briefly yesterday. The most obvious one would be as a diffusion process or some kind of contagious process or spillover process, competition. There are a number of theoretical models out there that form the basis for this type of specification. Or we can think of it as a data problem where we filter out the effect of spatial autocorrelation. And just in a little more detail than I showed yesterday, we first move the spatial lag to the left-hand side. Then, since this is a matrix product with the same vector, we bring it together as I minus rho W, and I minus rho W is the spatial filter. So in words, what this is for each observation is the value at a location, say, or location I, minus parameter rho times the weighted average, the sum over j, wi, j, y, j, the weighted average of the values at neighboring locations. So you take the neighbors, you average them, you multiply that by the rho, and take it out of what you observe at the location I. You take it out of it, that's called filtering. It's like detrending. The difference with detrending is that you don't know what rho is. As I mentioned yesterday, the value of 1, which would be like a first differencing in space, 1 is not part of the parameter space, so you can't actually use first differencing in space. So then, in practice, it doesn't really matter whether you do the filtering or you do the estimation of the model, because you need to estimate the model to get the filter coefficient rho anyway. So it's a matter of interpretation. In practice, you end up estimating rho and beta jointly. So you can think of the filter, if you knew what rho was, you could filter first and then run a regression of the filtered variable, say y star, on the x as, say, a standard least squares regression. But as it turns out, and we'll talk about that more tomorrow, because of the endogeneity, you cannot just do this. You have to estimate them jointly, and then after that, you can construct the filtered variables and, say, make a map of them or something like that. But they're not actually used in the estimation process, which is different from, say, a first differencing in time series, where you then use the first differences in the estimation process. The other interpretation, and we already saw an example of this, uses the reduced form, which is essentially solves out the simultaneity. So the WY is endogenous, simultaneously determined with the actual Y. So in order to find the Y's, we need to get rid of all the endogeneity on the right-hand side. So the way we do this is we move, as before, the WY over to the left-hand side. We use these inverse matrices to then get the pattern of the Y as a function of the pattern of the X's pre-multiplied with this inverse, as well as the pattern of the error terms pre-multiplied with this inverse. So this is the reduced form. What this tells you is that the value of Y at I is a function of X at multiple locations, as well as the error term at multiple locations. So if we do a house price model, the price of our house is a function of the characteristics of our house, but also our neighbor's her house and our neighbor's neighbor's house, as well as the unobserved factors that end up being in the error term for our house, as well as our neighbor's house and the neighbor's neighbor's house. So it's actually a very complicated thing. It ties a lot of things together. And it also gives us this notion of a spatial multiplier. Because, well, I shouldn't say because. With the proper structure of the weights matrix, particularly if it's rho standardized, and since the parameter rho, not the rho, but the parameter, the autoregressive parameter is less than 1, we have this power expansion that we can do. So then the inverse, we actually don't, and this is a trick we use in our software, we don't actually make the inverse, compute the inverse explicitly, but we can approximate it to any desired degree of precision by using this power method. So we just simply power the weights matrix, and we actually don't even do that, because if you look at this carefully, this is a product of a matrix times a vector. The vector is the change in the x. But that's a spatial lag. So if you know how to construct a spatial lag, W times that vector is the spatial lag of that vector. So then W squared times that vector is W times the vector. So it's the spatial lag of the spatial lag. So if you have a fast procedure to compute the spatial lag, you just recursively keep computing the spatial lag of the spatial lag of the spatial lag, add these all together, and the sum of those approximates the inverse of the full matrix. So you never have to invert the matrix. You never have to actually multiply a matrix. You just use the sparse spatial lag operation, which is the one, for example, in GeoDa. The spatial lag in GeoDa never uses all the zeros. It just looks at the non-zero elements, picks out the matching locations in the y vector, and multiplies them through. And so if you do this very efficiently, then even for very large data sets, 100,000, 300,000, this is not a very complex operation. It's simply a few multiplications and then additions. So you can approximate the inverse of 100,000 by 100,000 matrix by a series of these powers, and it's nowhere near 100,000. After about 40, you get a precision of up to 8 decimals precision, which is much more than most people want. So rather than inverting this huge monster, you do 40 of these power multiplications and you're there. And that's the way you approach this in practice. Now it also illustrates very nicely how the spatial multiplier works. If you do a change in the system, the delta x, the first effect is the direct effect, if you wish. That's the identity matrix. So I paint my house, it affects the price of my house. But it also, in the second round, affects the price of my neighbor's house. Or, if you wish, the delta x goes beyond I, it goes to W. Through W, it goes to the first order neighbors. But it's not as strong. It's not as strong because it's pre-multiplied by the row, which is less than 1. Okay. And we move on to W squared, which are the neighbors of my neighbors. And it's even less strong because now it's row to the power 2, which decreases even more, and so on. So it spreads through the system, but the effect gets weaker and weaker as we move further and further away because of the powering of a value of a parameter that is less than 1. And this is exactly what Tobler's law is about. Everything is related to everything else. We have the full inverse that gives us the covariance matrix, but closer things more so. As we move further and further away, the powering of the parameter that's less than 1 decays the effect. And so we end up with, for all practical purposes, after about 40 or so neighbors, depending on the value of rho, it's 0. But that's much further than in our moving average process, where it stopped after 2 neighbors. After 2 neighbors, we were done. What happens if we ignore the spatial lag? I mentioned this briefly yesterday, and I won't dwell on it again, but it's good to reinforce it because this is the essence of the problem. It's an omitted variable problem, and essentially, if the neighbors matter in our specification, they should be in the specification. If they're not, then everything we do will be wrong. And in fact, we saw yesterday, and I'll show you the graph again, the estimate is wrong. The curves get centered on the wrong value. The variance is wrong, so significance tests will be off. Sometimes the sign is off, and it doesn't always happen, but in some examples, and this is very important for policy purposes, if you estimate a model, say the effect of education is positive, right? But then there really is a lot of interaction going on, and you have ignored this interaction factor, so then you bring it in, you re-estimate the model, and all of a sudden the effect of education becomes negative. Because the original estimate was in fact inconsistent. It had, crudely put, it has no connection whatsoever to the true parameter value because it's inconsistent. So when their interaction is important, you need to model it. If you don't, then everything you do is wrong, basically put. Okay? And we saw that yesterday with this graph, that as we're cranking, now we know how to do this, you know, we draw a random sample of 100 standard normal variates, we pre-multiply it by this inverse matrix, and we get spatially correlated variables. Then we run the regression as if we didn't know about this, and this is what happens to beta. As rho goes up, the beta moves out, and its variance around its estimate increases as well. So by the time we have rho 0.9, it's centered around 1.2, and the true value of 1 is way in the tail of the distribution. So it's almost not even there. So we're totally off. And that's the bottom line. When there is strong interaction in the spatial lag model, you have to incorporate it in the model. And as we saw yesterday, the spatial error model is a slightly different story. It's more about precision. And a spatial error model is one with a non-diagonal error covariance matrix. And as I mentioned yesterday, this non-diagonal, off-diagonal elements being non-zero, in and of themselves, that's no big deal. I mean, that's just non-zero covariance. Where it becomes interesting is where the structure of this covariance has some spatial structure, some spatial meaning. And earlier this morning, we saw some examples of this. But here we have the situation flipped around. See, earlier this morning, we started with the process, and then we ended up with the covariance matrix. Here we have a covariance matrix that is spatially structured somehow, and we try to incorporate that in our model, specifically in a model for the error term. So for example, we'll be interested in finding out whether a simultaneous autoregressive process for the error term gives us a covariance that matches the covariance that we observe. Or is it a moving average process? Now these two covariances are not the same. So we will have a problem tomorrow of specification testing and of comparing models, different models for the error term. One could be autoregressive, one could be moving average. How can we tell one from the other? How do we estimate these models? That's what the spatial error model is about. But it's a problem of precision more than a problem of consistency, because as we saw yesterday, and I'll show it again in a few minutes, we stay on target on average. The spread increases. So we become less precise. And if we ignore that fact, then our t-test will be wrong, and so on. Now, if we take that into account, then we're fine. So there's actually nothing wrong with using least squares. You still get an unbiased estimate. However, the estimate of the standard error of the beta hat, if you wish, has to be adjusted to take into account the fact that you have spatial correlation. And typically you don't do any adjustment. You just crank the standard program and out comes the estimate with the t-test and so on. Now if you, and we'll cover this in the Frontiers course, there is actually a way to construct a heteroscedastic and spatial autocorrelation consistent covariance matrix. It's a mouthful, but it is a way to run OLS, stay with the unbiasedness of OLS, and adjust the standard errors for the possible presence of autocorrelation. Just like you may become familiar with the White adjustment for heteroscedasticity. So the same thing, you can stick with the OLS, but you adjust your standard errors to reflect the fact that you have heteroscedasticity. Now typically what we will be doing is not stick with OLS, but go to a model that incorporates the spatial autocorrelation explicitly and estimate a mixed regressive spatial autoregressive model, or a model that has this kind of structure in the error covariance matrix. Now, one thing that I want to point out to you, and this is running ahead relative to tomorrow, is, as we just saw, the covariance matrix has this nasty inverse in it for a spatial autoregressive process. So we have the sigma squared I minus rho W prime I minus rho W inverse gives us the covariance matrix. Now, if you remember generalized least squares, or feasible generalized least squares, which is the way in which we treat covariance matrices like this, and we'll see this again tomorrow, the estimator includes x prime variance inverse x. So in the estimation, we actually use the inverse of the covariance matrix. In this case, the inverse of an inverse is no longer an inverse. So this is good, because this will give us a way to estimate this without having to do these inverses. Break? No power? Cassette. Okay, we'll have to switch the thing. Just a 1 minute pause. This is going to be a great editing job. Where did we switch the cassette? The trick, I should tell you this, if you want to listen to this, we actually have, for those of you who were late, we have the voice with the synchronized slides from yesterday. The way to listen to this is played at double speed. It's very doable, but it makes a 2-hour lecture a 1-hour lecture, and it's very efficient. You should try it once. You can still understand everything. And a lot of these slides, they're not actually moving, so it's not like watching a soccer game or something where everybody runs at double speed. But the slides don't move, the voice goes at double speed. It's very understandable. And if you're really good at it, so you can crank it up even faster and turn a 2-hour lecture into a 15-minute tape or something like that.
Sounds like a sci-fi movie.
Well, it's sci-fi. It's not sci-fi. You know, people do this. Students actually do this. What is it called? Apple has this i something university. Yeah, on the iPod, iTunes U is called. And it's a number of universities tape lectures and turn them into podcasts. This is what we do as well. And you can do it very quickly. In fact, I can do this almost instantaneously, and then they give the podcasts to the students who listen to them in between classes. And they listen to them at high speed, which is something that us older folks might not think of, but it is very doable.
I had a blind coworker who had a reading program for mail and reports, and he had his cranked up so fast that to most of us it sounded like gibberish, but he had just adjusted.
Yeah, it's all training. You can do a lot more than you think. Okay, so the autoregressive errors are actually the simultaneous autoregressive process, even though it seems more complicated at first take because the covariance is more complex. It has this inverse in it. For estimation purposes, it's actually better, because if we look at this running ahead to tomorrow, what this will mean is we have this I minus lambda W, which essentially will give us a spatially filtered variable. So once we have an estimate for the lambda, we have a spatially filtered variable, and then we can just do OLS, which is essentially what the estimation is about. In contrast, the moving average process, which has the simpler covariance function, because there is no inverse in it, in the estimation has an inverse. And so to carry out feasible generalized least squares for a spatial moving average process requires you to invert an n by n matrix at every iteration. Why is it that nobody uses moving average processes for the error? This is why. I mean, this is my take on it. There's other reasons too, but it's very hard to do. For small toy data sets, you don't have to worry about it. You can do the inverses. But once you get into 100,000 or more observations, this is not trivial. And this is not, this one doesn't have the power expansion that we used before. So we actually have to do this. And so it's basically not very practical for very large data sets to do it this way, and then we have a solution. The solution is, because this is a local process, we can resample. And when we resample, and we say it's a first order moving average, we know that if once we move two more out, they're uncorrelated. So if we have 100,000 observations, we take a subsample that is not spatially correlated, and we run the regression as is. Now, what does this mean? It's a loss of efficiency, which means that our standard errors will be larger, but that's exactly what our estimation process does. Our estimation process adjusts the standard errors to properly reflect the fact that these are correlated. If we resample uncorrelated ones, we have a smaller sample, which means less information, greater imprecision, or larger standard errors. So we get at it in another way. This is, of course, not practical if you have an autoregressive process or if you don't have a really large data set. Because for very large data sets, the inefficiency, the loss of efficiency can be negligible. You will still have tens of thousands of observations. Yeah, and that's still a lot. But if you have 49 and you start resampling, you're in trouble, okay? Because you end up with 10 uncorrelated observations, which is not a practical thing to use. So the other thing that I mentioned, and I just want to illustrate this some more here, is that all these spatial processes induce heteroscedasticity. If we look at the diagonal elements, it's actually easiest to do this for the moving average model because we don't have to do an inverse. You see that the diagonal elements are 1 from the diagonal from the I, from the identity matrix. The parameter times 2 times WII, but by construction that's 0. So that doesn't count. And then this other term, which is the diagonal of WW prime. And with a little bit of algebra, you can see that this is the sum of the squares of the weights. So if the weights are not the same, then these sums will be different and we have heteroscedasticity.